Welcome, guys. So in this video, we can start to prove the inverse function theorem, and I hope you. So this is part of my analysis lecture, and follow routing apostle, and almost quite finished. And I already talked about the differentiation of multivariables and the contraction principle, and also some basic idea. So inverse map. So basically contain all of these, we are allowed to prove the inverse function theorem. And I will prove the inverse function theorem in this video. In the next video, we prove the implicit function theorem, and the next we prove the rank theorem. And basically we finish the order. I think this is the most important theorem in the analysis. Hope you guys subscribe to my channel. So I will use some lemma that I proved in the previous video, like contraction map or something. So if you don't know about it, I will I will post the list so you can go to check. Okay, so yeah, so now we can prove the most I think it's very non-trivial theorem in the advanced calculus, so inverse function theorem. So I think this theorem that the people usually use in the calculus, right? So let's say let me just talk about the statement. So suppose let's say f is this prior mapping. So this notation why invented previous time, but basically this is just say that the f prime is continuous. F prime is continuous, so differentiation is continuous. Remember that. So, okay, so now f is a open set of between Rn to Rm. So f is a multivariable. So differentiation means that it's I already say it's a linear transformation. Okay, and so condition is that f prime of a. So for some points now it's matrix is invertible. So this is the condition. So the condition says that the differentiation at that point is invertible, and then define b to be f of a. Then we have the following. A. So the first thing say that there exists the open set. U is open set of A, and also V. Let's say V is in R. Okay, so now it's invertible matrix, right? So it should be unbiased. So V is an open set also in n dimension, and so there is this open set of open cover of A, and then V is open set in Rn, such that F is 1-to-1 and on2 is 1-to-1 on U. And basically Fu equals to V. V is open. Okay, so basically it's 1-to-1 on2 on U. Okay, so this theorem just tell you that basically just tell you that if you have A, which is invertible, that means at the very nearly A this point, you can find the open set U, such that this open set you map this open set F into a F of A, where it is V, and such that F restricted on this V and U. So if you only focus on this U and the corresponding V, then F is an invertible function. There's inverse of F, right? Because F is 1-1 on2 on U, Fu is V. Okay, so this is, remember V is open, right? If V is not open, then otherwise I can just define F to be F of U, then it becomes onto, right? So the key point is that V is open. Okay, so B says that if G is an inverse of F, right? So now I can define G, right? G is the inverse of F. By definition, FV, okay, defined by, then I can so basically this G is inverse of F, means that G of F of X equals X. Then G will become this. So basically the G prime is continuous. Okay, so it means that this inverse function theorem, just simply speaking, is that if the differentiation is invertible, if differentiation at some point, a is invertible, the function has inverse locally. Okay, so the simple example, the calculus, right? If you draw a circle, right? So you can compute the differentiation. So for example, in let's say x choose to be this point. So in this point, the differentiation is non-zero, right? So you can locally, if you shrink very small, then you can locally see that in these parts there's a local inverse. Right? Actually, in all the upper parts there is a local inverse except for these points. Right? For this point, right? Because the differentiation is zero. So if you take this part, right? So this part look like this. So whatever you choose is so small, it's not, there's no inverse, right? Because there's always some points which is the same as this point. So you can view this circle as y equals to f of x if the differentiation is non-zero, right? So locally you can choose very small region. Okay. So basically this is the inverse function theorem. Okay, the proof is very non-trivial. Okay, so proof. Okay, so yeah, so let's say fa prime is a. So remember that a is a n by matrices. I already said many times, and f is a multivariable function. Now, the key point is that how to choose v, right? So the idea is that how do you choose a open set u such that this will work. So this is a trick. Okay, so one can choose lambda such that 2 lambda times the inverse of the norm of a will be 1. This is a trick, right? Since a is invertible, so you can compute the inverse and you can take the norm and take 2 lambda a inverse to be lambda. Okay, so this is the key. Oh, and also this is continuous, right? So basically, there is this open ball, right? U, which is a subset of E, such that f prime of x minus a, right? So this guy is continuous. So now this is a key part that since we use is continuous. So let's say undone for all x belongs to u. Okay, so this is our u. Right? I pick u in E such that u cover a. So u is some open cover such that for all x belongs to u, such that f prime of x minus a less than lambda, right? So this is the condition for all x belongs to u. And u is an open ball, right? So basically a here, and there's open ball u, and such that f prime of x minus a less or equal to lambda. Okay, by continuity of this f prime of x, such that I choose lambda to this. So this is the important step. Once this step is fixed, then I think the proof is easy. Okay, so now you can define phi of x to be x plus a inverse y minus f of x. Okay. So basically you can so let's say given any y, so given any y belongs to Rn, and then you fix x. Given any y belongs to Rn, you can find a function. You can define a function phi of x such that this defined to be this. Okay, so notice that f of x equals to y if and only if phi of x is x. So phi of x, x is a fixed point if only f of x is equals to y. Okay, and also, okay, you can check that the differentiation respect x. Just do the differentiation. You get the identity minus 1 a prime of x. Just a inverse a minus f of x prime of x. Okay. Okay. So now a minus f prime and a inverse compared to this, right? So this guy is less than lambda if I take absolute value, and this guy is less than this, right? So these tell me that phi prime of x, the norm of the phi prime of x will less or equal to a inverse norm times the lambda, which is half. Okay, so since the differentiation is less or equal to half, right? And the U is convex, right? Because U is a ball. So which tell you that 5x minus 5y less or equal to half x minus 1. Okay, so this is the trick that we will use. Okay. Okay, so now from here that you obviously you can see what you can see that this is a contraction map, right? So contraction map must be 1-1, right? So phi is a 1-to-1 map. So which tell you that f is a 1-to-1 map because phi of x equals to x if only y equals to f of x, right? So f is 1-to-1 map. Very nice, right? on U. So basically now we already proved the first part, right? We already proved the first part that there exists an open set, which is open ball on A. Now I just define V to be f of U, right? So that will be onto. So the final part is that I want to prove it's open. So I just define, right? Then it will be onto. So remaining is to show that, so we only need to show V is open. Yeah, okay, this is not difficult. Should be very simple. So let's say I pick V to be f of U, and let's say pick Y0 to be V. Okay, I want to prove that there exists a ball such that all points in that ball can be find a point in U such that f of U equals to that point, right? This means open. Okay, so I know that Y0 is f of x0, right? By construction. And I want to find a ball, right? So let's say I find an open ball, B is open ball of at the center at x0 and the radius r greater than 0. And now I can find it very small such that the closure, right? Because x0 is in U, right? So U is open, right? So I can find find a ball which is small such that B closure less subset of U. Okay. Okay, so now I choose B bar. So there's a radius, right? I can choose a radius R such that B bar, subset of U. Okay, so the key, so I will prove the following. So I claim Y belongs to U whenever Y minus Y0 less than lambda times R. Okay, so R is the radius such that the B bar less than U. And I claim that if there is a such R exists, then Y minus Y0 less than lambda will make Y belongs to V, which proves that V is open. Okay, so yeah, setting. So let's prove this. So phi x0 minus x0, right, is a inverse Y minus Y0, right? Because remember that it's just this, right? So you put x0 f of x0, right? So get this, which is f of x0 is y0. Okay, so now you take a norm. Right, so lambda r. Okay, r divided by 2. Okay, so now let's say for any points which x, let's say x belongs to B bar, I pick any point x belongs to B bar, and 5x minus x0, I take norm, will be equals to 5x minus 5x0 plus 5x0 minus x0. So this guy is bounded by r divided by 2. And this guy is bounded by half, right? Half times x minus x0 by the previous results. Right? X minus x0 by definition is less than r, right? So it's less than r. Okay. So which proof? So what this means? What this means is that this phi of x minus x0 less than r, right? So which tell you that phi of x is what? Belongs to B, right? Because B is a radius r. Okay. So now belongs to B, so belongs to B bar, right? So B bar is what is closed, right? B bar is closed. So phi is a contraction map on closed set, and then which is compact, right? Because it's closed ball. So by the completeness, or basically the theorem of the contraction map on the complete matrix space, this phi of x has fixed point, right? Has a unique fixed point. Okay, so basically phi has a fixed point, So here is his point in B bar, right? So that means there exists x such that the phi of x equals to x, which give you y equals to f of x. So basically there exists x such that y equals to f of x, right? So basically you choose y, satisfy this, and then you use the contraction map, powerful results of a contraction map to find such x. Okay, so this is the proof. So so one y equals f of x means that V is open. Okay, so yeah, this is the proof for the A. Okay, so let's say proof B. So to prove B, yeah, so to prove B, choose the inverse of f is trivial, right? Because the inverse function already exists, and they define to be this. So the only non-trivial parts that we need to prove is its differentiation is continuous. This is the most tricky part. Okay, so proof B. Let's say let me just pick y belongs to V, right? So and y plus, let's say y plus k belongs to V. By the way, these are vector, and by definition, right? So now V, F, and U, F econ U will map to V, right? And this is 1, 1 on 2, right? So there exists X belongs to U, X plus H belongs to V, that belongs to U, such that right, y equals to f of x because it's on 2, and y plus k equals f of x plus h. Okay, so now let's compute phi x minus h minus phi of x will be h plus a inverse f of x minus f of x plus h. Where is h, right? Plus minus a inverse by definition is k. Okay, so easy to, let's just bound this, right? So h minus a inverse k is bound, is a vector, right? It's bounded by h times half. Okay. Why this is true? Why this is true? Because remember that 5x minus 5y is bounded by half x minus y, right? This is my condition, so you use this. Okay? So h minus a inverse k is bounded by h divided by 2, which tell you that a inverse k is greater or equal to h divided by 2. Okay, which tell you that, so let's see, so I have a inverse k, right? Greater or equal to h divided by 2. So that means h is less or equal to 2a inverse k, which is less or equal to 2a inverse to the norm of this times k, where is k divided by lambda. Okay, by definition. Okay. Okay, so there's a theorem that I think I proved. So there's a theorem that I proved in a previous video. Basically, it's a theorem says that let's say that there is a theorem says that if B minus A inverse norm is less equal to 1 minus A inverse, then B will be invertible. Okay, so if you don't know the proof of this theorem, you can just go to my previous 2 or 3 videos. and I will list basically, yeah. So basically you use this theorem, right? So this theorem tell you that if you are so close to some invertible matrices, sorry, this is a sorry, if you are so close to some invertible matrices such that your difference is less or equal to 1 over a inverse of that invertible matrix, that guy will be invertible. Okay, so which tell you that what? Who tell you that now this difference, right? This difference h, let's say from here, is so close, right? It's very close, close than 1 over the node, right? So which tell you that it's invertible? Okay, so which tell you that f prime of x has inverse. Okay, by this theorem, right? Have its inverse. Let's say t. Okay, so that means let's see. So let's see. Let's say I should say the differentiation has inverse, right? So g is the f inverse, right? But let's say differentiation results is t. Okay, so that means gy plus k minus gy equals minus tk, right? By definition, this is what? This is just f, right? So f of x, right? So it's inverse map, right? So it should be h minus tk is minus t fx plus h minus f of x minus f prime of xh. Okay. Hopefully it's easy to see this. Let's see why this is true. Right. So h minus tk, right? So let's see. Right. But you can see that your y plus k, right? So k is basically f of x plus h minus f of x, right? So you can just plug this into this, and your t is inverse of f prime, right? So t f prime is 1, right? So you can take this h to be this term. Okay. So let me just write things down. So k is f plus f x h minus f of x, and t f prime is 1, right? So h, it can be written as a t f prime h minus tk, or t f of x plus h minus f of x. Okay, so you can take t out, so it's minus t f of x plus h minus f of x minus f prime of xh. Okay, so now I have this. Okay, so I want to prove it's continuous, right? So what I should do, right? Just divide it by k, right? So let's divide it by k. Right, so by definition, it's less or equal to t minus lambda fx plus h minus f of x minus f prime of xh divided by h. Okay, so let's see why this is true, right? By the previous, I have this, right? So I take norm, I divide it by k, right? And by the previous results, I know that h is less or equal to k divided by lambda. So I can get this one, okay? Okay, so let's take k to be 0. Okay, so k to be 0, what? Means that h to be 0, right? Because h is bounded by k, so h goes to 0. But h goes to 0, this guy exists, right? By definition, right? By definition, because f is f prime, f differentiation is what? Is continuous, right? Okay, so yeah, so this guy exists. This guy exists. This guy tends to be 0, right? Because it's differentiable, right? So goes to 0. So which proves that basically prove that g prime of y is just t, right? Because by definition, g prime of y is t. Okay, so you know that this is guys just its inverse derivative, right? So g prime of y is basically f prime of g of y doing the inverse. Okay. Okay, so now we prove that the inverse map differentiation is the same as what we expected. Okay, so finally, so we know that G is continuous, right? So since G is continuous, mapping from v to y, v to onto u. The reason is y is continuous, right? Because g is differentiable. Right, remember in the previously that we just proved that the g prime y is t, which is g prime is differentiable, right? So it must be continuous v onto u. And we know that the f prime is continuous of u into a set into, let's say, omega, which is all the invertible function from n by n. Okay, and this inversion is continuous, right? So this inversion is continuous. So this inversion is continuous. This is how I also prove. So basically, if you want to invert a matrix, right? If you use the Cramer rule, then only consider determinants, which is all the polynomial function. So invertible is continuous. Okay, so and also there's a previous theorem. Let's see what is it? Oh, yeah. So this guy inversion is continuous, and f prime is continuous, right? But because f belongs to this, so continuous and this guy continuous, right? So which proves that g prime is also continuous, right? Because g prime, I mean, you have formula for g prime, right? So g is f inverse, right? So you have a formula of g prime, which you, let me just check again. Right, so your g prime of y is basically f of prime gy. Right, take inverse, right? So this is continuous, and its inverse is continuous. So g prime is continuous. So we prove that the differentiation of g is also continuous, which proof B. Yeah, so this is the proof of the inverse function theorem. Basically, I just follow the routine. Okay, so let me just take a recap. So idea is that you try to find u, right? You try to find u such that f is a one-to-one on u, and you define v to be onto, and you need to prove it's open. Yeah, so this part is not using the contraction map. So this is one theorem, and the second theorem is that you need to prove its differentiation exists, right? But this use the topology of the matrix. Right? Okay, so if you are so close to some invertible matrix, then you must be invertible. And using this, you can prove the differentiation exists, and you prove that differentiation is actually G differentiation. Then you use the composite of continuity property to prove that the G prime exists. Yeah, this is the powerful inverse function theorem, which is a big theorem in the I think it's a big theorem in the advanced calculus. Okay, so maybe in the future maybe I take some break, and I may prove the implicit function theory. Okay, so see you guys. Subscribe to my channel.